In this video, I look at different ways of performing simple error detection and correction. We have an L dash bit string. Bits are numbered from 0 to L dash minus 1. Okay. A simple idea that occurs to us is to add I to the, if the ith bit is 1, to add I to the sum and take the sum. Of course, since 0 does not affect it, so we could add from 1 to L dash. The sum, if all of them are 1, will be L dash into L dash plus 1 by 2. But we know due to the commutativity of addition that 2 plus 3 can be written as 1 plus 4 and so on. So if two different bits combinations will still add up to the same sum, and even if you keep the complement, it will be nothing but L into L dash plus 1 by 2 minus S. So the other is true. So the other alternative is to note the number of ones R, and to find this sum for a particular value of add I plus 1 to the sum if the ith bit is 1. Then the second, and maintain another sum, add I plus 1 square to the sum if the ith bit is 1. Then may add I plus 1 cube to the sum if the ith bit is 1. As you can see, you can try and solve it. The probability that a square plus b square equal to c square plus d square is very, very small. Like this, for again, choose a small value c. For up to c values, you can maintain I plus 1. If the ith bit is 1, you can maintain I plus 1 power j, to add I plus 1 power j to the sum, for j varies from 1 to c. The probability that the sum matches will be virtually 0. You can use this for data compression also, but decoding it will take a lot of time, might take a lot of time. But it can certainly be used for error detection and correction also. So if you any attempt at trying to do error detection and correction will also automatically give rise to data compression, and any efforts at trying to perform data compression can also be used for the purposes of error detection and correction. Another possibility is to use something like an odometric coding, wherein you code the actual indices of those bits which are 1. So you have L dash bits here, 0th bit up to L dash bit. L dash minus 1th bit. Okay. For all those bits which are 1, you note their ordinals or indices. So if you have c equal to log of L dash, assume L dash is a power of 2. Okay. So L dash equal to 2 power c. So all the indices of all those bits will turn out to be something like this, ordinals like this. So there will be c here. So note the number of ones that occur, number of values ones that occur for the ith bit of c, leftmost bit. Second bit, number of ones for all of this up to c of these. Then take pairwise combinations, 4 possibilities. If you take this and this, 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 and note how many of those 4 possibilities occur and how many of those belong to each of those 4 possibilities for these 2 combinations, and then this and this. So clearly you will have c minus 1. This should itself be sufficient. This binary combination alone itself should be sufficient because of the transitive nature of this. If you take this and this, you know what the count is, and you know this and this, you know what the count is, and you know this and this, you know what the count is. You might be able to infer or deduce what the count is for this, this and this. So you might be able to say, so you can keep this also as a method of by inclusion and exclusion. You might be able to, so you might not have to take more than a very large combination for this, 2 or maybe 2 and 3 or something like that. 2 should be sufficient is what I feel. So this is also another possibility you can use for performing error detection and correction, and also it might also help in performing coding or data compression, which would offer very high orders of data compression.